by that concrete slab, which results eventually in fatigue damage. Here's an idea that came from Europe, the widened slab. This is a brilliant, amazing idea that makes design so much less costly, because you're basically adding half a meter here or even less, and you keep the wheel away from that free edge. And that's a huge difference in stress and in deflection at the joints, dowel bars, and all of that. You can come up with a 30% thinner slab with this design. And that's caught on a lot now in the States. And another interesting thing is the friction, the contact friction between the slab and the base course. If you put a cement treated or an asphalt base, that friction is really important. You want to bond those two together, have like a monolithic composite slab there. And so this procedure can handle that. You can model the load transfer at the joint. This is a small dowel bar, 25 millimeters, and you can see it's kind of deteriorating over time. So maybe a little bit larger reduces that bearing stress, reduces the deterioration. This is just taking that model that you just saw and comparing against independent data from the Asheville road test site. And here is slab thickness, 200 millimeters up to 325. The cracking, this transverse cracking is dropping way down, as you see. So you can pick wherever you want, the amount of cracking, pick your design. Here's faulting, here's the dowel diameter, here's the faulting. This is a lot of faulting right here. You really feel this as you drive over. It's not good. The public would not be happy at all with that. So you want to have a bigger dowel bar in there as an example. But it's predicting well. And then here's reliability. I just wish I had more time. I did my thesis on this many years ago. And it's an exciting thing to design for different reliabilities. And for farm to market, maybe you're down here. For high urban freeways, you know, where the risk of failure is high, or the consequence of failure, a lot of political complaints. You don't want that to happen. You build it thicker, stronger, bigger bars, things like that. So it's optimizing based on conditions. Okay, now just in closing, a couple of examples here. For example, the state of Indiana in '09 did the entire year. They designed their concrete and asphalt pavements with the old method, the old AASHTO, totally empirical, versus the new AASHTO, which is mechanistic empirical. And they found some interesting things, which I'll show in a moment. I'll show you a 40-year design for a project that I was just involved in Salt Lake. I'll show you a new concept on design, and the 100-year design in California. So here's the Indiana. Here is the layer thickness. I'm sorry, this is in inches, but this would be 30 centimeters right here. The old empirical design guide. Here is the new ME design, which we've been talking about. Here's a one-to-one line. In the thinner sections, these are quite close, actually. But as you get thicker, and a requirement is thicker, you can see how ultra-conservative this old procedure is. It just is crazy. Building airport pavements is what this is, 18 inches. It's ridiculous, of concrete or asphalt, wherein you really need much less than that. So by tailoring us to the field conditions, it has brought about a major savings, millions of dollars. In fact, all the research gone into this effort could be saved in one project, one single big urban freeway like this. Here's a project in Salt Lake City I was involved with. It involved an old asphalt pavement that had been built up over many, many years, deteriorated asphalt. 40-year design on the concrete overlay. Existing asphalt was deteriorated. It was going to carry now 57 million trucks to travel over those many years into the future. And the pavement was deteriorated. Here's a few cores. Well, one good one, but then you see a lot of deterioration. So there's a damage factor built in that reduces the modulus of the asphalt down to a much lower number, which is there because it's stripping, it's debonding, things like that. So this, after going through the design process, this is what came out with, was 30 centimeters of concrete, 4.5 meter spacing, and a 38-meter diameter dowel bar. Over about 18 centimeters of hot mix, over an aggregate base that was there over a week. This was a very weak subgrade. So that was built, and that was a very successful, and we assumed the bonding, we milled it, and we cleaned it so that we had good bond between the two. Hopefully will last 40 years. And we then, the dowel bars, took out the two center bars because you really don't need them. They're not needed. Just these in the wheel paths is all that is needed. And that's what it looks like today. There's like 6 lanes here in one direction. Well, it's a very major type of a highway, but there are lots of these being built in the U.S. today. Lots of concrete is being built. Okay. 2 more quick examples. This is going to the extreme other end, Farm to Market Road. This project is 16 years old. It's carried about 2 million trucks. And it has these short joints. They're like half the lane, about 1.8 meter between the edges here, and 1.8 meter in this direction. A little bit longer, maybe that was 2 meters. So you're really sawing it up into small joints. I think this came out of Chile or some projects in Europe, but this is now almost one of the most popular kinds of design in the U.S., and it's very competitive with asphalt overlays. So we're talking here in the order of 15 millimeters over so whatever, asphalt there, and it's bonded. There's no dowel bars. There's tie bars, yes, tie bars, but not dowel bars. There isn't hardly a single crack in this pavement, 0, after all these years. The state of Colorado has built many, many hundreds of miles of this kind of pavement, and other states are building them even on heavier traffic. But, it's definitely low and medium trucks. When you start getting into really heavy, like that last design, you start worrying about faulting developing. Good bond between the two. This is a project, the Pan American Highway in Chile. This is their standard design. This is just in the truck lane, but it's the same joint spacing and the same thickness. So it's very competitive they can beat asphalt by 10% on any project they have to do a comparative bids on. So it's a hot thing. And now one more topic, 100-year design. California, one of the engineers there had this brilliant idea, well, why don't we look at a 100-year design? Because the procedure can literally go out that far. Maybe it's not very accurate, but it can design out that long structurally, not durability-wise. Now you have to really deal with durability, but in the valleys of California, there's not a lot of frost freeze thaw damage. So durability has never really been a problem in California. But the reasons for 100 years, and once we started meeting on this and we thought, let's bring in some environmental people. Let's bring in some material resource people, and let's see what they think of this idea. And they were extremely interested, extremely supportive of it. Pretty soon there was a room filled with 25 people talking about a 100-year design. Any of you professors out there, this is a great exam question for any students in your class. How do you design, how would you provide a 100-year design? When you start thinking about that, it kind of blows your mind. You have structure, you have durability, you have all kinds of issues. But anyway, these are some of the reasons. I'll just let you read those. There's so many reasons, but it really boils down into longevity is crucial for sustainability. The longer that structure lasts, the more sustainable it is. And so California is really looking into this, and we did, Professor Harvey at the UC California came up with life cycle costing, and it wasn't that much more. For the first cost, it was a little more, 5%, 10%, but long term, it was less, most of them, either similar or less because of, and that was just the agency cost, not even looking into all the user delays, all the CO2 and all of that kind of thing. So there was many benefits to the traveling public. Many lane closures, if you think about it, lane closures over 100 years, well, lots of them, and some very long-term lane closures, versus if it's a 100-year design, you're just out there grinding and regrinding and grinding and regrinding. Okay, well, I hope this has been interesting. It's kind of a long and winding road. We've gone up and down and around, but we've arrived at a better place technically, and I think we can build some really reliable and cost-effective types of concrete pavement. So thank you very much. I hope that's been enough.
Thank you so much. Extremely interesting for us in Sweden, having such an expert from US. Thank you, Mike. Excellent. This is a small piece. It's not a large volume concrete. This is a small volume concrete.
Thank you.
Thank you so much.